So today what I'd like to do is to take just a couple of minutes to finish up some ideas from Chapter 1, and we'll be talking about molecular geometry, and particularly bond angles. And then what I'd like to do is to move on to Chapter 2, where we'll be discussing acids and bases, and particularly their relationship to organic chemistry. And just as in Chapter 1, where we took concepts that were familiar from general chemistry, but gave them an organic flavor, and began to think about, in the case of Chapter 1, structure and bonding in organic molecules, we're going to do the same with acids and bases and begin to get to see the relationship to reactivity in organic chemistry. And at the very end of Chapter 2, we'll begin talking about, actually even throughout, we'll begin talking about this very central concept of curved arrow notation that I've talked about. Well, let's take a moment to finish up our discussion of molecular geometry. And we got a little bit of this when we were talking about orbitals and sp3 hybridized orbitals and so forth. And I just want to go through very explicitly. And let's start with sp3 hybridized atoms. So sp3 hybridized atoms have about 109 degree, roughly a tetrahedral arrangement of ligands and lone pairs. So let's say about 109 degree bond angles and a tetrahedral arrangement of ligands and lone pairs. So we started by talking about methane before. Pardon? Oh. We started by talking about methane before, so that's where we'll begin right now. Here's methane. We have an sp3 hybridized carbon. And remember, we're going to think about the arrangement of ligands, the substituents on that carbon. So we would describe the geometry of methane as tetrahedral. By that I mean you have 4 substituents around carbon, and if you look at all 4 of those substituents, they form the corners of a tetrahedron. In fact, in methane, all of the bond angles are equal. They're all 109.5 degrees. This is what the geometry of a tetrahedron dictates. If we move across the periodic table from carbon next to nitrogen, then to oxygen. We'll skip fluorine, that's just going to be linear. We get next ammonia, and I'm going to draw the lone pair of electrons on top like so. Here's our hydrogen. Here's another hydrogen. And here's another hydrogen. If we just look at ammonia and forget about the lone pair for a moment, NH3, and we just consider the arrangement of atoms that you see. In other words, you don't really see the lone pair. In fact, often when we draw ammonia, you sort of write NH3. and forget about it, we'd say that ammonia makes a pyramid structure where the nitrogen sits on top of a pyramid of 3 hydrogens as the base. So we would describe it as pyramidal molecular geometry, even though the arrangement of ligands and lone pairs collectively is tetrahedral. The lone pairs of electrons take up a little bit more space than the pairs of electrons that are in a bond. That makes sense. The electrons in the lone pair are sort of spread out. In a bond, they're more focused between the 2 atoms. As a result, that crunches down ever so slightly on the hydrogen-nitrogen-hydrogen bond angles. And so the hydrogen-nitrogen-hydrogen bond angles are just a little bit under 109 degrees. They're 107.3 degrees. The exact numbers aren't too important in organic chemistry. They'll sometimes make a little bit of a difference, but you can think of it as 109 if you don't want to remember separate numbers. As we continue to move across the periodic table, then, we get to oxygen and hence to water. And I'll draw the 2 hydrogens on water in the plane of the page and try to represent this molecule in 3-dimensionality by trying to show one lone pair coming out off the oxygen and the other lone pair going back. And so if we just look at the atoms, if we just consider the hydrogen, oxygen, and hydrogen, we'd say this molecule is bent. The trend of the lone pairs of electrons taking up a little bit more space continues, so the hydrogen-oxygen-hydrogen bond angle is crunched down just a little bit more, 104.5 degrees. All of this falls into something that you've learned in general chemistry, probably. Who's heard the name BSEPR theory or valence shell electron pair repulsion theory? So this is just a review of BSEPR theory as applied to types of structures in organic chemistry. And of course, what you'll see is as we move on from molecules like water, which are in the realm of inorganic chemistry, to molecules like methanol or dimethyl ether, which are in the realm of organic chemistry, the geometries stay the same. In other words, if instead of having a hydrogen here, we had a methyl group making methanol, CH3OH, we would have a bent geometry around oxygen. And if instead of having a hydrogen here, we had another methyl group making dimethyl ether, CH3OCH3, we would also have a bent geometry. All right, we've seen some sp2 hybridized atoms before. sp2 hybridized atoms have about 120-degree bond angles and a trigonal planar arrangement of ligands and lone pairs. We looked at ethylene last time, and we were concerned with an orbital-based model of the structure of ethylene. We remember that we said the molecule ethylene is planar. Like so. Each of the carbons is sp2 hybridized. And the carbon-hydrogen-carbon bond angle is about 120 degrees, as is the carbon-hydrogen bond angle. Let's take a look at another organic species. Let's take a look at the methyl carbocation, CH3+. What's the first thing you notice about the valence state of the methyl carbocation? Doesn't have a complete octet. That carbon is very unhappy. In fact, you will never see a naked methyl carbocation in reactions in this class. You will in some cases in the gas phase. You may, for example, under special conditions in mass spectrometry. You will, however, see other carbocations where instead of having a hydrogen, you will have carbon atoms on the central carbon. And in fact, in this week's discussion section, you'll see the tert-butyl carbocation, which, like the methyl carbocation, doesn't have a complete octet, but is a little bit less unstable. So the methyl carbocation is also planar, trigonal. We have an sp2 hybridized carbon. We have 3 ligands around the carbon, no lone pairs of electrons, 120-degree bond angles, hydrogen, carbon, hydrogen. Methyl carbocation has a vacant p orbital, meaning that it has a p orbital with no electrons in it. That p orbital is orthogonal to the plane, so I'm now drawing the methyl carbocation like so. And here's our vacant p orbital. Thoughts or questions?
So we have 6 electrons in bonds with hydrogens, and then 1 electron in...
0 electrons. So you bring in a carbon, 3, which has 4 electrons, 3 hydrogen atoms. That would give you 7 valence electrons. But you take away 1, you have 6, and a net positive charge. So, and in fact, we drew the species, let's see, we drew boron, no, we drew a fluorinated carbon. Well, if you think about boron, and you take a boron compound with 3 ligands on it, you also have a vacant p orbital on boron. So the carbon basically has been reduced to coping with not having enough electrons. Take one more example we saw last time, formaldehyde. Maybe we saw it the previous time. Exact same situation as ethylene. The carbon is sp2 hybridized, and the oxygen also is sp2 hybridized. You have 2 lone pairs of electrons on the oxygen of formaldehyde. All right, last bit of geometry I want to talk about, sp hybridized atoms. sp hybridized atoms have approximately 180-degree bond angles and a linear arrangement of ligands and lone pairs. Let's take a look at a few examples. We talked about acetylene before. H, C, triple bond, CH. The carbons in acetylene are sp hybridized. You have 180-degree hydrogen-carbon-hydrogen bond angle on both sides. Take a look at another molecule. See a new functional group here. Let's take a look at acetonitrile, CH3. Whoops. CN. I'll draw in the lone pair of electrons. As I said, the name of this molecule is commonly referred to as acetonitrile. The carbon and the nitrogen are sp hybridized. And the arrangement of the bond angle about the central carbon, the carbon-nitrogen bond angle is 180 degrees. Let's take a look at one more molecule, the molecule allene, or 1,2-propadiene. Allene is the common name for this molecule. You'll learn more about nomenclature when we get to systematic names, or more about the systematic nomenclature when we get to systematic names. Don't sweat for right now. The question was, would you rather we know IUPAC or common names? So the IUPAC name of a molecule like acetic acid is ethanoic acid. You'd probably never hear anyone in class talk about ethanoic acid. It just wouldn't roll off the tongue. But you might see it, particularly if you have a substituent on it. But then you'd recognize it. You'd say, oh wait, yeah, I know propanoic acid and butanoic acid. So right now, don't sweat. Go with the flow on some of the more common terms we're getting. All right, allene's a very funny-looking molecule. We haven't seen a molecule quite like this with a carbon double bonded to another carbon and on both sides. But of course, we've seen a structure like this in carbon dioxide, with carbon double bonded to an oxygen on one side and double bonded to an oxygen on the other side. Now we have a little bit of a chance to think about hybridization. The central carbon is sp hybridized, and the outer two carbons are sp2 hybridized. And the carbon-carbon-carbon bond angle is 180 degrees.
What makes it like
makes it less than 180 or more than 180 degrees? Well, we saw exactly the situation with lone pairs where you can have unequal substituents. A lone pair on one side takes up a little bit more space. Now, in the case of 180, you're not really going to have that circumstance coming up here. But, for example, in formaldehyde, if the hydrogen-carbon-hydrogen angle was a hair under, well, that wouldn't even be a good example here. So basically, ligands, lone pairs can take up just a little bit more than ligands. There are also cases where there are some really interesting variations in hybridization, and this is the stuff that makes chemists scratch their heads. So, for example, I talked about carbon dioxide. If we concatenate and add another double bond here to an oxygen, that molecule actually has a little bend to it. And that's the sort of thing that makes chemists at a very advanced level say, why is this? We have simple rules, and then we see there are some exceptions. And the exceptions are often the fascinating thing that get people at an advanced level, well beyond sophomore organic chemistry, to get excited about it. All right, well, let us move on to chapter 2 now, and I want us to begin talking about acids and bases in organic chemistry. Acids and bases are central to organic chemistry, both in the generation of reactive species, species that we call electrophiles, nucleophiles, and also as reactive species in their own right. So this is why it's very important for us to think about acids and bases. And as I said, we'll use this also as a springboard for learning curved arrow notation. throughout the course of this week, we're going to start to see what this means. And then, of course, because this concept is so central, it will come back to us again and again. We're going to see, for example, that what we've known of in general chemistry as Lewis acids, species that react by accepting a pair of electrons, are very similar, in many cases the same as what organic chemists call electrophiles, things that want electrons. Species that we think of as Lewis bases in general chemistry, species that react by sharing a pair of electrons, are what organic chemists call nucleophiles. I should close my parentheses. And in many cases, we're going to simply see protons coming on, protons coming off in organic chemistry. Let's start. There are a number of different models, correct models, for acids and bases. Let's start with the model you certainly learned first in general chemistry and in high school chemistry, what's often referred to as a Bronsted acid or Bronsted-Lowry acid. The definition of a Bronsted acid is very simple and intuitive. A Bronsted acid is a proton donor. And conversely, a Bronsted base is a proton acceptor. And so we think of a general Bronsted acid-base reaction as a Bronsted acid and a Bronsted base react together to give the conjugate acid of the Bronsted base, another acid, and the conjugate base of the Bronsted acid, another base. What do I mean? Let's take HCl, hydrogen chloride. Hydrogen chloride is a gas. When you dissolve it in water, they react. You have an equilibrium. That equilibrium happens to lie very far to the right. You form H3O plus and Cl minus. In this reaction, the HCl acts as an acid. It donates a proton to water. The water thus acts as a base. We form the conjugate acid of water, H3O plus, so I'll say that this is an acid. And we form the conjugate base of HCl, namely chloride. So I'll write that this is a base. Thoughts? We can write this reaction's in equilibrium. As I said, it happens to lie far to the right. In other words, if I wanted to amplify on this, I could draw a longer arrow on top and a shorter arrow on the bottom. But we can also write the reverse equilibrium. Chloride anion plus H3O plus is in equilibrium with HCl and H2O. In that case, we'd be saying a base plus an acid is in equilibrium with the conjugate acid and the conjugate base. Let's start to think about the mechanism of this reaction and the flow of electrons. And now we're going to use our organic chemist notation of the curved arrow. So I'm going to now draw the water very explicitly. I'll draw all bonds and lone pairs of electrons so we can see how bonds are made and how bonds are broken. I'll do the same for hydrogen chloride, remembering to draw in my 3 lone pairs of electrons around chlorine. The water takes the proton off of hydrogen chloride. Electrons flow from the lone pair of electrons on water to the proton, to the Bronsted acid. We can't have 4 electrons around that hydrogen, so electrons get pushed back onto chlorine. You'll notice how I draw my curved arrows. I always start at a source of electrons, a lone pair or a bond, and I always end up on an atom. And when all is said and done, the sharing of this pair of electrons with the hydrogen results in a new bond. We have a formal positive charge on oxygen, positive charge on oxygen. And now we get our chloride anion. We have 4 lone pairs on the chloride anion. Now, as I hinted before, what's really powerful about this type of way of thinking is we can see all sorts of analogies. For example, if instead of using water in this reaction, instead of adding hydrogen chloride gas to liquid water to get aqueous hydrochloric acid, which is a solution of hydronium ion and chloride in water, if instead I had done the same reaction with methanol, CH3OCH3, we can predict what would happen. Methanol looks a lot like water. The only difference is we have a methyl group instead of a hydrogen. We still have an oxygen, it's still sp3 hybridized, we still have a lone pair of electrons, and the other component in this equation is the same. So it shouldn't be a great leap to be able to predict that we should see a similar reaction in which electrons flow from the lone pair on methanol to the proton. We push electrons back onto chloride. We set up an equilibrium. We get protonated methanol and chloride anion. Let's try another example. And again, I'll show the comparison between concepts that we get in general chemistry and concepts that we get in organic chemistry. Let's take the ammonium ion, NH4+. And we'll allow it to react with the hydroxide anion. Again, we have an equilibrium. The ammonium ion acts as a proton donor, in other words, as an acid. The hydroxide anion acts as a proton acceptor, in other words, as a base. The hydroxide anion pulls a proton off of the ammonium ion, and we can use the same concept of the curved arrow to demonstrate this. We have electrons flow from the hydroxide anion lone pair to the proton on ammonium. We push the electrons from the bond onto the nitrogen atom. Now we generate ammonia. There's our lone pair. Ammonia is the conjugate base of the ammonium ion. And we generate water. Water is the conjugate acid of hydroxide ion. Let's try the same reaction with an organic compound. We'll try this reaction with methylammonium ion. And we'll still use hydroxide anion. Now it should be very easy with all of these examples to predict what hydroxide anion does. Pull the proton off of the methylammonium ion. We push the electrons onto nitrogen. We have an equilibrium. We get water and methylamine. You'll often hear of this reaction referred to as making the free base of an organic amine. You can have an amine hydrochloride salt, for example, generated by reaction of an amine with hydrochloric acid. When you add a base, like sodium hydroxide, you'll pull that proton off the ammonium ion to generate the free amine. You've heard of this term, making the free base from an amine salt. Where have you heard of it?
Cocaine.
Cocaine, exactly. And when you hear of cocaine being free base, what that means is using a base like sodium bicarbonate to generate the free base of cocaine, the physiologically active form. So not only is free base a noun, but by popular usage, it has ended up becoming a verb. All right. Now, and in our next lecture, we're going to be discussing the degree of acidity, position of equilibria. And in order to measure the degree of acidity, or to characterize, to describe the degree of acidity, we'll often use the term pKa. pKa is a fancy way of saying negative log of the acidity constant, Ka. Ka is the acidity constant or the acid dissociation constant. And all that means is if you have an acid, we'll call it HA, and you put it into water, you set up an equilibrium of dissociation, an equilibrium between the hydronium ion and the conjugate base, A minus. Our equilibrium constant, remember how you get that? That's just the concentration of the product multiplied out of the concentration of products over the concentration of reactants, ignoring anything that's constant concentration like solvent. So in other words, Ka for acid dissociation equals the concentration of hydronium ion times the concentration of the conjugate anion divided by concentration of HA. Put simply, that's the pH you'd get of a 1 molar solution where half of it is HA and half of it is A minus. So if you take half a mole of sodium acetate and half a mole of acetic acid, dissolve it to make a liter of solution, and measure the pH, you'll get about 4.56, the pKa of acetic acid. A strong acid is fully dissociated, a weak acid is partially dissociated, and what I call a very weak acid is essentially unmeasurably dissociated. So one thing to keep in mind is pKa is a log scale. What does that mean? That means a change of one pKa unit corresponds to a change of tenfold in acid dissociation constant. A change of 2 in pKa unit, or a difference of 2 pKa units, corresponds to a factor of 2 of 100 in acidity constant. So if at one end of the scale we take a look at HCl, a very strong acid, HCl has a pKa of -7. In other words, that means that Ka equals 10 to the 7. At the other end of the scale, the weakest acid, and I'll use that term very loosely, that you would ever see would be something like methane or another alkane. The pKa of methane is 50, positive 50. Ka equals 10 to the negative 50. What that means is if I dissolved a mole of methane in a liter of water, you would not have even a single molecule of the methane that's dissociated. It is such a weak acid, it is, in the context of general chemistry, only an acid in name in that you could write an equation, but the equilibrium of methane and water to give methyl anion would be completely to the left. You would see no dissociation. So, in other words, what we're saying here is that HCl is 10 to the 57th. I can't even wrap my head around such a big number. 10 to the 57th times more powerful acid than methane. Thoughts or questions? A great question. Why are we moving the lone pair of electrons from the base to the acid? So we're beginning to think about organic reactivity. We're beginning to think about the making and breaking of bonds. And the making and breaking of bonds is all about the flow of electrons. When we form a bond, we make a new shared pair of electrons. When we break a bond, we give up a shared pair of electrons. And showing the curved arrow shows the flow that makes the bond. All right, we will pick up next time talking about acid strength and look at various